Welcome back. In this segment, we're going to define a concept that is related to the big O notation, and that concept is called the big omega notation. Simply put, a big O relationship states the fact that a function is an upper bound for another function, while the big omega notation states that a function is a lower bound for another function. So these concepts are strongly related. Let's provide a formal definition for the big omega notation. So let's say f and g are numerical functions, that is, their domain is either the set of integers or the set of real numbers, and their codomain is the set of real numbers. We say that f of n is big omega of g of n, so this symbol here is the uppercase version of the last letter of the Greek alphabet called omega. So we say that f of n is big omega of g of n if there exist positive constants c and k such that the absolute value of f of n is greater than or equal to c times the absolute value of g of n, whenever n is large enough, meaning n is greater than some constant k. So that is the official definition of the big omega notation. So notice the only thing to change in this definition to get the big O notation definition. So in other words, to go from omega here to big O, you just have to change the greater than or equal sign to a less than or equal sign. So another way to emphasize this contrast is to remember how we define the big O notation and what it actually means. So f of n is big O of g of n means what? Means that f is asymptotically dominated by g, meaning g grows at least as fast as f when n gets large enough. In other words, g is an upper bound for f. Another way of saying that is that f is bounded above by g up to a constant factor asymptotically, just to remember the details. So, what's the difference with the big omega notation then? Well, we say that if f of n is big omega of g of n, then the reverse is true. That means f is not dominated by g, but actually f dominates g asymptotically. That means f grows at least as fast as g when n is large enough. In other words, g is not an upper bound on f in this case, but g is a lower bound. Another way of saying that is that f is bounded below by g, up to a constant factor asymptotically. So just keep in mind these almost opposite concepts of big O notation and big omega notation. If you want an upper bound on a function f, you use the big O notation. If you want a lower bound on a function f, you use the big omega notation. So a result that follows directly from this discussion is the following fact. If f of n is big omega of g of n, that is, this relationship holds, then that's equivalent to saying that g of n is big O of f of n. An easy way to give you the intuition for that is to realize that since c is a positive constant, it's not equal to 0, we can divide both sides of this inequality by c, which is this c will disappear, and here we have a constant factor in front of f of n, which is 1 over c, which is also a positive constant. So by the simple algebraic manipulation, we just infer that g of n is less than or equal to a constant times f of n when n is large enough. And that is exactly the definition of g of n being big O of f of n. And so the observation is that if one function is big omega of another, then the second function is big O of the first one, and vice versa. These two statements are equivalent. Let's conclude this segment with a concrete example of a big omega relationship and how to prove it. So let's prove that the function f of n defined as follows is big omega of the function g of n equals n squared. So all we have to do is to prove that f of n is greater than or equal to a constant times n squared. Now, to make the proof easier, I'm going to assume that all the values n, f of n, and g of n are positive, so I'm going to drop the absolute value functions in the definition of the big omega relationship. So the observation here is that we already have an n squared function in the definition of n, of f. So all we have to prove then is that this quantity here is greater than or equal to 0 when n is large enough. And that's pretty easy to do. For example, if n is greater than 1, then 5n is greater than 5. We can subtract 3 from both sides of the inequality. And we just prove that in this case, this quantity is positive because it's greater than 2. So in conclusion, f of n then must be greater than 11 times n squared when n is greater than 1. So we just found two witnesses, namely c is equal to 11 and k is equal to 1 to prove this big omega relationship. And that concludes our proof.